We are making a functional foam board wing, which will be put to a bending and a torsional test. We will have to comply with the requirements and not exceed them. The process starts from already made wings, and we adapt them by doing sketches with pen and paper. These ideas are then transferred to Excel to make spreadsheet calculations. Once everything is correct, we go do our design on SolidWorks. Finally, we experiment, repeat the process, and make iterations until fully optimized.
For the design of our spar, we made use of the Excel spreadsheet to calculate the optimum height, width and thickness. Using the calculated moment, direct stress and structural reserve factor to evaluate the direct stress at a given location along the spar, and using the torsional compliance and torsional stiffness reserve factor to evaluate the torsion at a given location, allowed us to decipher the best possible dimensions for our spar. As for the rest of the wings components, we created a model on SolidWorks using the design data from our spreadsheet. We were able to transfer the data for the rib shape from our spreadsheet to SolidWorks to create the aerofoil, which from there was used to create the rib, as well as being able to model the leading edge spar, rear spar and flaps, which can then be assembled and used for simulation.
After designing using the spreadsheet, we use SolidWorks to simulate the behaviors of the spar under load. Under 2.5 kilograms, about 24.5 Newton of load on the wingtip, the results show that the stress is mainly located near the root and the tip is not affected. With 30 Newton-meter of torque on the wingtip, the top and bottom surfaces experience more stress than the sides, as you can tell by the differences in the color of the model.
After our spar passed the requirements in the Excel document, we needed to test using practical experiments. To carry out these experiments, we needed to create a sturdy base for the spar. We 3D printed a sleeve for the spar and to hold it securely during the bending and torsion tests. To test if our spar met the torsion requirement when a max load was added, we made another component to hold a ruler to which masses could easily be applied. The deflection was recorded and the angle due to deflection was calculated. The experiment used a similar setup, but this time the masses were added to the beam's tip. The deflection of the beam tip was recorded as each increment of the mass was added. Thankfully, our design passed both tests and we can now move on to mass reduction.
Based on the simulation results, we can reduce the mass of the spar by removing the material from the least stress part. We make 3 designs: rectangles, circles, and rhombus. Rectangular hollows have the largest displacement and rotation angle among the 3, and seconds are circular hollows. The rhombus has the smallest bending displacement and smallest rotation angle, which make it the best option to carry out the experiment.
Our next steps will be to build more iterations of the spar and attempt to make further weight reductions. We will experiment breaking the spars until we have found one that will break after meeting the load specified and will comply with the maximum torsional degree. After we have done this, we will be ready to assemble the whole wing together and put it to the final test.